Welcome to Statistics for Surveys, Session 2, Descriptive Statistics Tables, Segment 3, Scale Variable, Frequency Density. In this session, I'll try to explain the concept of a frequency density. It will be helpful if you're familiar with the terms absolute frequency and relative frequency, as well as the term ordinal and scale variable. In this segment, we'll be discussing the terms class size, upper and lower bounds, frequency density, and relative frequency density. If we have a scale variable and would list all the possible values with the corresponding frequencies, you might sometimes end up with a frequency table like this one. I'll zoom in a little bit, but as you might be able to notice, there are 847 people who are aged 18, but this list becomes so long that it doesn't become clear. And one of the points of descriptive statistics is to give a clear overview. So instead of giving a long list like this, what is often done is that the scale variable is converted into bins. For example, here these ages are binned into these different bins, sometimes known as classes, but I'll use the term bin. So we can see that, for example, 2,810 people have an age somewhere between 15 and 21. To some extent, these bins, they are actually forming now an ordinal variable. A few notes about creating bins though. The left side of the bin, the lower one, is sometimes known as the lower bound, and the highest end is known as the upper bound. The number of bins that you create can either be determined by using some form of a formula. I usually say myself as a rule of thumb between 4 and 12. In an optional segment, I'll go a little bit deeper into those. For now, what is important is that no matter how you choose your bins, it should be so that they do not overlap, so that, for example, if you say 10 but under 15, then your second class shouldn't be something like 12 but under 18, because then somebody who is 14 years old would actually go into both of these bins. Another thing is that everybody should be able to fit into at least one bin. Let's have a look at another example. Here we can see that 23 people are of the age range of 10 but under 15. And let's say this is the number of people who are in the age of 10 but under 15 who are willing to buy our product. As we can see, most people in this example are 40, which is the age range of 25 but under 15. This indicates that we should perhaps focus on this age range. Here's another table. In this table, we can see that most people in this case who enjoy our product, 45 people, is in the age range 10 but under 25, which is different than the previous one that we saw where it was 25 to 50. Even more perhaps strange is that both of these tables come from the same larger table. If you look here, the 25 but under 50 is in this new table the same as the combination of these two groups, and indeed 29 plus 11 is 40. Well, if we look at the other table on the right, the 10 to 25 is the same as these two groups combined, and 23 plus 22 is indeed the 45 that we saw here. So depending on how you pick your bin sizes, you can actually manipulate how many people might fit into that category, and based on that make another decision. So we need something to resolve that. Instead of looking simply at which bin has the highest frequency, we can also see which bin is actually the most crowded, also taking into consideration the size of the bin. You might be familiar with the term population density, which is often used to compare elements of different countries, which is the population divided by the area. Now we can use this same technique for our frequencies. Instead of population, which is the number of people living somewhere, we have frequencies. So we substitute the word population by frequency. Instead of area, we have bins, or actually bin sizes. So frequency density is nothing else than the frequency divided by bin size. The bin size in itself is the upper bound of the bin divided minus the lower bound of the bin. Here's an example of how this can be calculated. So, for example, for the age group 0 but under 10, we have an upper bound of 10 and a lower bound of 0. So the bin size becomes 10 minus 0 equals 10. We're given that the frequency is 15, so the frequency density is that 15 divided by the bin size, and that gives us 1.5. In general, you can say you take the frequency divided by the bin size and you get the frequency density. If need be, we can also reverse this process. So for example, if we know that the frequency density is 2.2 and we know that the bin size is then 10, then we can simply multiply the 2.2 by 10 to get the 22 again. To understand what the frequency density actually shows, we'll focus on this 1.5 for now. Notice that we have an age category of 0 but under 10, but we can split this up into classes or bins actually of size 1. So these 10 bins together, they actually are the same as 0 but under 10. Their total frequency should then also add up to the frequency of 0 but under 10, 15. So if you think about it, that means that each of these 10 bins should then have a frequency of 1.5, which is exactly the frequency density. And indeed, if we add them all up, we then get 15. We can then actually define the frequency density not by how it's calculated, as most textbooks do, but have more of a conceptual definition that the frequency density is the frequency in each new bin that can be expected if a bin is split into bins of size 1. So if we split the age bin 15 but under 25 into smaller bins of 15 but under 16, 16 but under 17, etc. till 24 but under 25, then we would expect each of those newer bins to have a frequency of 2.2. We can apply this same technique to the relative frequencies to actually get relative frequency density. For example, here's a table, and to highlight, I've already calculated the relative frequencies, which was the frequency divided by the total. Now, to calculate the relative frequency density, we again have, for example, the age category 0 but under 10. We split this up into 10 different bins, because then we have a bin size of 1 each time. And all of these together should now have a relative frequency of 0.14, which means that each of them should actually get a relative frequency of 0.014. So if I fill that for each of them, then together it forms 0.14 again, and that's why the relative frequency density is 0.014. Instead of taking the density as our main goal for the relative frequency density, you can also perceive it as from the relative point of view. So here's another method to actually calculate relative frequency densities. In this case, I don't calculate the relative frequencies, but I'll simply have a look at, I already calculated the frequency density in itself, and since relative means in relation to a total, we'll simply divide the frequency density by the total frequency. In this case, that's 1.5 divided by 105, which gives me 0.014. Note that these results in the end will be exactly the same as in the previous method. A few final notes on frequency density. Note that if the bin size is the same for each category or each bin, there's not really a point to calculate these frequency densities because you'll simply be dividing each frequency by the same number. And usually you're trying to compare these with each other, so you're simply dividing by the same number, and the largest number stays the largest, the ratio stays the same, etc. So there's not much of a point to do this if the bin sizes are all the same. You might be tempted to also calculate cumulative frequency densities or even cumulative relative frequency densities, but they're not so often used and sometimes even argued to be pointless. I will therefore not go into these in this course. There is, however, an alternative method to use to calculate frequency densities by using a so-called standard class size or standard bin size. I'll discuss that in an optional segment to not let this session run too long. The last point is, however, that sometimes you have open-ended classes like 65 or older or below 20, and you can't then really determine how big the size of that class is. You should then therefore either decide that it's impossible to calculate frequency density. Some textbooks will say that you can multiply the previous bin size by 2 or 1.5, but that's really arbitrary and you should be very careful in doing so.